Dzień dobry Państwu, Łukasz Warzecha. To jest rozmowa niekontrolowana, jak Państwo widzą, w dosyć niezwykłych warunkach, innych niż zwykle. A to dlatego, że dzisiaj mam niezwykłego gościa, z którym będę rozmawiał po angielsku, dlatego reszta rozmowy będzie w tłumaczeniu. Bardzo dziękuję Fundacji En Arche za zorganizowanie tego nagrania. A moim gościem jest dzisiaj pan Michael Denton, który może być Państwu znany przede wszystkim z tej książki, choć oczywiście jest to tylko jedna z wielu książek Michaela Dentona. Kryzys, teorii, ewolucji, napisana jeszcze w 1985 roku i właśnie o tym będę z moim gościem dzisiaj rozmawiał przede wszystkim. O tym, co właściwie dzieje się, co jest nie tak z teorią ewolucji. Michael Denton, biochemik, który zrobił doktorat na King's College, jest związany z Discovery Institute, teraz pracuje w Nowej Zelandii. Hello.
Pleased to be here.
Nice to meet you. Mr. Denton, first, usually when evolution theory is discussed, especially in Poland, some people are prompt to say that this is the church which wants to overthrow the evolution theory, and this is a very well-established theory. But this is not obviously your case. You are not a clergyman, obviously. Can we clarify the situation? What is your, general point of view?
Yeah, well, basically, I'm a skeptic about Darwinian causation. Darwin claimed all the order of the biological world, or the most of it, came about by natural selection. I seriously doubt that is actually the case. I think there's a lot of order in biology which cannot be explained in terms of Darwinian natural selection. But my grouse against Darwin, if you want, is purely scientific. I can honestly say that I have no interest in defending any religious grounds. So my skepticism about Darwinism comes from scientific only. That's what, I have no religious, agenda.
Let's try to explain first things first. Can you explain the difference between a theory and a hypothesis? Because when we speak about Darwin, we speak about Darwin's theory. Yeah. What's the difference in general in science between hypothesis and theory?
I consider that scientific hypothesis and scientific theories, they're close. I mean, I tend to think, a scientific theory is something that's, it's an ongoing model of the world, and you're looking for new empirical evidence for its support as time goes on. When exactly a theory becomes a fact is an interesting question. But certainly in the case of Darwinian theory, it's still very much a hypothesis or a theory, awaiting substantial validation, which, as far as I'm concerned, is never going to come. But yeah. But a theory is something that's it's something in progress. It's something that's awaiting some further confirmation, further empirical confirmation, if that makes any sense to you.
Yeah. So when Darwin formulated his theory, it was in the middle of the 19th century. Since then, we can say that we have been waiting for a strong confirmation of it. Some people, nevertheless, today tend to say that this is not a theory, this is actually a fact. This is a completely established truth. Are they right?
Well, what they're probably arguing is that some form of evolution is established. I mean, there's been life on the Earth for 4 billion years, and there's a succession of different life forms as you go from the ancient times to the present. So there's been some form of what you might call evolution, right? But the Darwinian model explanation for evolution is natural selection, and so evolution is more of a description of a pattern of things. There's all sorts of different variations of what evolution might mean to people, okay? But Darwinism is about causation. It's the claim that the order of biological systems throughout time was the natural selection was the engine of evolutionary change. That the evolution of life on Earth was caused by Darwinian natural selection. But the idea of evolution is something different to the idea of how it was caused. And Darwinism,
it's a very important thing that you are saying right now. I think lots of people don't understand that.
It's completely different, yeah. I mean, for example, in one sense, evolution is very close to being a fact, one sort of evolution. I mean, the fact that there's changes in life from 4 billion years ago all the way through the Jurassic dinosaurs, early age of mammals. And so in that sense, a form of evolution is sort of a fact, okay?
But the question that we were asking is, what caused it?
Yes, but Darwinism is a theory about causation. The causation. Darwin claimed that, in fact, natural selection was the major engine of evolutionary change. Yeah.
So he claimed that the weaker or the weakest died without, leaving any trace, and only the stronger or the strongest remained.
Yes.
And this was the cause of the evolution. Am I
yes, no.
Summing it up right?
You summed it up correct, yes. It's survival of the fittest. That's what he called it. And what you've described is survival of the fittest. Yeah.
And what made him think that this was the cost? I mean, that famous journey of his. Why was he so convinced after coming back from it?
I mean, the famous voyage on the Beagle convinced, I think, he became convinced of evolution. He thought there had been a certain degree of biological change. And he imagined, for instance, that the animals on the Galapagos Island had somehow were related to animals in South America, and had somehow got to the Galapagos Islands, and on the Galapagos Islands had undergone a degree of evolutionary change. So I think that what Darwin saw on the Beagle was evidence for evolutionary change. The theory he sort of invented to explain the change was natural selection. That matured in Darwin's mind later than the voyage on the Beagle. So he saw evidence for evolution, if you want. Then when he went back to England, he was thinking everything through. He hit on eventually the idea of natural selection as the causation of evolution.
And I think this is also a very important point. And in fact, I have to admit, it's even a little bit, perhaps not of a surprise, but of a new thing to me too. I mean, he observed some facts on the Galapagos Island, but he did not observe anything that could give him then any thought about how it happened. He thought it through after coming back home.
Yes, I think he might have had some inklings when he was on the Beagle, but the development of his theory of natural selection came when he got back to England and started thinking about everything he'd seen on the Beagle and so forth. And the idea of natural selection came to him. It also came to came to Alfred Russel Wallace as well. As you know, these two came. Wallace and Darwin both hit on the idea of natural selection as a causal, as something that could cause evolutionary change. But definitely, yes, evolution as a pattern is quite different to the actual causation that Darwin said. And of course, there's other models of evolution. There's Lamarckian. There's laws of form. There's a whole lot of other alternative causation theories of causation, apart from natural selection. But the theory he promulgated was, of course, natural selection.
So if we find some weak points in Darwin's theory, it's not actually about what he saw on the Galapagos Island. These are facts. They are established. Yeah. It's about the method, how he tried to explain this.
Yes. I mean, basically, I think, myself, you can explain a lot of the diversity on the Galapagos Islands by natural selection. The question arises is natural selection a universal asset? Will it explain everything? And I would say very definitely, I don't believe it explains everything at all.
Well, and that's why I wanted to ask you about this famous book. This is your, I think, first book that was written in 1985, am I right? Or published in 1985.
Yes, a long time ago.
A long time ago, but this is definitely the most famous book of yours, at least here in Poland. What made you write this book? What made you be so much interested in this problem?
Basically, I began to doubt Darwinian natural selection when I was doing my PhD, studying the development of the red cell at King's. So, very simply, the development of the red cell involves a remarkable thing. It involves the enucleation, the final stages of the development of the red cell. The nucleus is ejected from the cell, okay? And it struck me that trying to explain how that could come about in terms of natural selection is very difficult, because a nucleus is either in a cell or it's outside of the cell, and the machinery for getting the nucleus out of the cell is highly complicated, and clearly that has to be there before the cell is ejected. So the question arises is, what causal factors in the development of the red cell would assemble a very complex cytological architecture to get rid of the nucleus? But until you've ejected the nucleus, you don't know what adaptive significance it has. So it struck me as being extremely difficult to account for this in terms of, natural selection.
But sorry, this was something that could be observed only when people got a possibility to see so tiny things, right?
Perhaps, yes. That's
so
right. Yeah.
in the 60s, in the 70s, certainly not in Darwin's time.
Yes. I mean, so basically, to cut a long story short, and it is complicated and technical, this, I found there were aspects of the development of the mammalian red cell which I found could not be explained in terms of Darwinian natural selection. First of all, I mean, the ejection of the nucleus is what you call a saltational event. It's a sudden event. It's not gradual. And there's no way you can imagine gradually, bit by bit, determining whether it's good to have the cell in or out of the cell.
It had to be just one step, one event.
It's like a saltation. It's not gradual. But there's other aspects of the whole process of mammalian red cell development which puzzled me very much. Birds have a higher metabolic rate than us mammals, and their demand for oxygen in their tissues is greater than in mammals, partly because flying is very energetic. And yet birds keep the nucleus. They don't get rid of it, right? So, then why did mammals get rid of the nucleus, you see? So it seems that, in fact, if birds keep the nucleus and they have a higher demand of oxygen than mammals, this is a very bizarre event now. It becomes more and more difficult to explain in terms of what you call adaptation. The more I studied it, the more I thought about it. I said, this whole thing can't be explained in terms of Darwinian natural selection. I can't see how this could ever be explained. That's still my view.
And when you started to express your doubts, what was the reaction of the scientific community?
Well, I used to discuss the evolution of the enucleate red cell in the corridors of King's and in the tea room, and nobody could give any explanation of how this happens. It was just a fact. But I thought to myself, well, the red cell carries out one of the most important physiological functions on the planet. It carries oxygen to our tissues from the lungs, right? And I thought, well, if this thing, the red cell, its enucleate state can't be explained in terms of natural selection, how that can't explain how it came about. Wow, what else is there out there? What else is there out there that can't be explained in terms of Darwinian natural selection? And that's when I started researching for evolution theory in crisis. And I found, well, there's a heck of a lot of other things out there which you can't explain easily in terms of natural selection. So yes, but that was the experience doing my research at King's, which set me on the long road towards evolution, a theory in crisis, evolution still a theory in crisis, working with the intelligent design movement, and having a fellowship with the Discovery Institute in Seattle. But it was that the puzzlement over that particular biological phenomena which set me on the road to there. Yeah.
How long did it take you from the moment that you realized something was wrong to the publication of the book?
I think it was about, I think the first draft of that was done probably 10 years after I left King's, something like that, yeah. So it was about a decade. But from being at King's, I was already thinking about these things, certainly, yeah.
And what were the reactions to this book?
From the academic community, pretty savage. if you want to know, yeah. It's surprising, you know, because basically the idea that in fact skeptics about Darwinism are some sort of, you know, tiny sort of minority in the biological world is not actually correct. There's a long tradition of first-class biologists that have never really been convinced by Darwinian natural selection. I mean, it started in the 19th century with Richard Owen, who was England's leading comparative anatomist. And then you get, just recently we've had Stuart Kauffman, who wrote a book called The Origins of Order, which is a brilliant book, fantastic book, right? And he's looking for self-organizing principles, all sorts of other principles, as well as selection. He also accepts that selection does do something, and I certainly accept that. I'm sure that selection was responsible for shaping the beaks of the Galapagos finches, for instance. I think Darwin was right about that. But selection doesn't have it's not powerful enough to generate all the order in the biological world.
So sorry, this is not a complete rejection of the selection theory.
Oh no. Basically, I think selection's a powerful organizing force, and I do accept this. But what I do reject is that it can explain everything. I don't think it can. I mean, you just take something like the origin of life. Being 80 has certain advantages. I can look back over several decades. And I've heard the story that we're going to solve the problem of the origin of life in Darwinian terms in the 50s, and then in the 60s, and the 70s, 80s, 90s, and here we are into the next century, into the third decade of the next century, and it's still not solved. And my prediction of the origin of life is it's never going to be solved in terms of Darwinian selection. Other factors were involved. So there's lots of other things like the origin of the feather, the origin of the amniotic egg. There's many things out there which have never been accounted for in terms of natural selection. So I mean and I mentioned quite a few of them in that book. Yeah. So from King's, 10 years later, I was preparing drafts of evolution. Yeah.
And since then, science has certainly progressed quite a lot. So what do we know more today in terms of evolution theory, in terms of intelligent project theory? First of all, in the terms of data.
In terms of data, basically, if you take the gaps in the fossil record, they still exist. In other words, basically, despite massive studies in paleontology, there's problems still. There's gaps in the fossil record. You can't go from one organism to another. And one of the people that's pointed this out quite strenuously is Stephen Jay Gould, the professor of he's deceased now, but he was the professor of paleontology at Harvard, a very prestigious post. And he was always pointing out the fact that basically there are persistent gaps in the fossil record. So studies in paleontology didn't join the gaps, right? And the sheer complexity of living systems has gone through the roof. I mean, it's just living things are so complicated. It's just amazingly how much more complicated they were than we thought of in the 50s when I was at King's. I would say that overall, all the advances in biological science since I wrote that book have provided no additional evidence to support natural selection. Yeah, and as I say, there's people like Kaufman, there's Goodwin, there's Newman, there's a variety of people sort of chipping around at Darwinism now quite seriously. And one thing that's come about is the realization that self-organization plays a big role in biological systems, ordering biological systems. For instance, the cell membrane, just as, I don't want to get too technical, but the cell membrane...
I think everybody understands that. Mm-hmm.
The cell membrane is perhaps the most important organ in biological systems. It encases the cell. But the cell membrane doesn't come about by natural selection or anything. The cell membrane comes about because of what you call the hydrophobic force of water. The lipids are insoluble in water. They're called hydrophobes. They don't like water. And so water forces them together to form the membrane around the cell. So that's the self-organization of matter creates the cell membrane, the most important organ in the cell. So that's one example of a very important...
So this is
and that is now known.
A natural feature of water without which no life could exist.
Oh, without the hydrophobic force, the cell would not exist. And when you look now at what we know about the basic chemicals in the cell, you can almost predict the design of the cell from basic natural forces now. And of course, if you can do that, you don't need natural selection. If things are arising from the properties of matter, like the cell membrane, and that's not the only thing that arises, a very important bond in living systems is called the hydrogen bond, which was first explored and discussed by Linus Pauling in his great text, The Chemical Bond. The hydrogen bond binds the DNA helix together, the alpha helix in proteins and other things. The hydrogen bond comes about because this is very technical, the electronegativity of oxygen and nitrogen. So this is another case where the basic properties of matter give rise to a very important type of bond in nature which binds the higher order structures of the cell together.
So we can, if I understand well, we can find in the very, tiny but basic features of basic things in the universe, we find the basis for life,
yes,
for the existence of life.
Yeah. There's almost now, I would say, as far as the cell is concerned, the key atoms, carbon, hydrogen, oxygen, and nitrogen, which make up 99% of the matter of biological systems, plus the hydrophobic force, plus the fascinating fact that when carbon and hydrogen combine, you get what you call a non-polar bond. And that's the basis of the lipids being insoluble in water. And there's such a lot of facts come to light since the molecular biological revolution, since the double helix, actually, over the last 60 years, and some of them since evolution theory in crisis, which suggest that there was a primal blueprint for the cell in the very properties of matter. And if you have a primal blueprint in the properties of matter for the membrane, for hydrogen bonds and so forth, you don't need natural selection.
These are very strong words that you're saying right now.
I'm telling you now. This is. I'm having a debate tomorrow, and I will be suggesting that I'm going to argue against the sufficiency of natural selection. And what I shall be arguing about, and one of the major points I'm going to make, is a vast amount of order in biological systems is constrained by the properties of matter or even enabled by it. For instance, as you're sitting there breathing now, the design of the lungs has two basic compartments. There's a conducting zone, which is when you breathe in and out. So you take the air in and out of the lungs by ventilating it. But there's another zone called the respiratory zone, right, where you can't move the air because the little conduits are too small, okay? And what happens there is it's diffusion. Now, because the diffusion of gases in air is very fast, and because air is light and has low viscosity, you can have a conducting zone and you can ventilate. And then because of the diffusion rate, you can carry oxygen, for instance, from the conducting zone into the alveoli and then into the blood. In other words, the actual design of the lungs in terrestrial vertebrates is highly constrained by the properties of air itself. And knowing the properties of air, if you were an alien on another planet and you asked, well, how do these guys on the Earth breathe? You would have a very good idea of how the lung was designed from the properties of air. And as far as the cell is concerned, if you know all the properties of carbon, hydrogen, oxygen, nitrogen, you know about the hydrophobic force and other things, you can make a good stab at the design of a self-replicating system like a cell.
Well, I have to say that listening to you, I really get some thrill, because it's like, you know, looking into the some mysteries of matter and of the world. It's a little bit like it brings to my mind the discoveries of the nuclear physics or quantum physics, where scientists look into it and they find some phenomena that are very hard to explain, but they know that without them, our world would not exist.
Yeah. I mean, this was Hoyle's famous discovery of the resonances in the beryllium, carbon, and oxygen atoms, which guarantee the synthesis in the stars of carbon and oxygen. Okay, it always amazes me, and it's a sense of wonder that we are stardust. The atoms of your body and my body were once in a star, and the only way they got out the star was by a supernova explosion. So there's a memory in our atoms of these amazing events. It's incredible. But once again, what Hoyle found is part, again, of what I'm talking about, a primal blueprint. That basically, the more you look at nature, the more you see a unique fitness in the properties of things for life on Earth. And once again, I want to stress that that doesn't mean that selection doesn't operate or doesn't do quite important things, but it's not the only engine of change in the biological world. Or it's not even a primary cause of the fundamental nature of things. Yeah.
Well, we have been talking about the weak points of the evolution theory, and now someone could ask, okay, so what's the alternative? Do you have any alternative explanation of how it all could happen?
Well, certainly, yes. I think that, in fact, when you look at the fine-tuning of the properties of water, the fine-tuning of the resonances in the stars, the fine-tuning of the properties of the carbon atom, and you go on like this, you suddenly find that there's what looks like, I'm not saying it is, you can't prove it, but it looks as if there's a design in this cosmos for biological beings like ourselves, written into the order of things from the beginning. Now, that design would not be exactly what we see on Earth, but it's highly constraining, okay? And it's called fitness. So there's a unique fitness in nature for carbon-based life, and there's also a unique fitness in nature for beings of our biology using oxygen from an atmosphere. And there's a lot of fascinating facts about this. First of all, oxygen, which is a gas. If you're gonna be a terrestrial being using oxygen, it needs to be a gas. It's not very soluble in water, and this means that the oxygen generated by photosynthesis is not lost to the oceans. It stays in the atmosphere for air breathing. Then we have a thing called nitrogen, which is a very powerful fire retardant, a fire quencher. It's so powerful that if you increase the amount of nitrogen in the mix of our atmosphere, a very small amount, it extinguishes all fire. You can't have fire, okay? And it's because the specific heat, this is complex, of the nitrogen atom, nitrogen molecule, is very high, and so it absorbs the heat. And so instead of the fire being able to easily move sideways away and spread, that spread is massively slowed down. It's not slowed down completely, as we have forest fires, obviously, but it's slowed down massively. And then not only this, you have a low reactivity of oxygen below 50 degrees. You know that, in fact, if you raise the temperature up oxygen becomes activated. In fact, what happens is molecular changes occur in the dioxygen in the atmosphere, which activate the oxygen, and it becomes more and more violent, more and more vigorous and it starts causing more and more fire. But so that's, and that prevents us from spontaneously combusting. Arthur C. Clarke said, why don't we spontaneously combust? It was one of the things that fascinated him, actually. We don't spontaneously combust in the presence of oxygen, this very, very reactive atom, because for some reason, I think it's something to do with the fine-tuning of the properties of matter for us, because below 50, it's not very reactive. And in fact, in the body, you can only use oxygen because transitional metals like copper and iron have just the right atomic properties to activate oxygen in the body. So this is a huge amount of fine tuning for the use of oxygen.
So many factors
it's incredible.
That must exist simultaneously. If any one of them did not exist, if I understand well.
That's right. I mean, for instance, photosynthesis, there's only one tiny region in the electromagnetic spectrum, from gamma rays all the way to radio waves, which has the right energy levels for photochemistry, and it's visual light. And guess what proportion of the sun's energy output is visual? It's about 40%. Just what you want. And the sun is a pretty typical star, so that's why when you look up at night and the stars, the whole universe is flooded with the light of life, the light for photochemistry. Yeah, these are just some of these amazing coincidences in nature.
But someone could say, and I hear that argument quite often from the part of the critics of the theory of intelligent project, that we are here just because all those factors exist together by chance.
Yeah.
That this is a chance.
Yeah. There's absolutely no way of proving that the degree of fine-tuning we see, which enables life on Earth and beings like ourselves, there's no way of proving that was there by design.
Sorry, can we calculate any probability of all those factors existing together?
Well, I think that most people would concede that it's very improbable. But then again, if you have a multiverse, if you've got an infinite number of universes, some of them will probably be like us. So I don't think. To me, I make the inference to design. Okay, I think sensibly it looks as if all this fine tuning is by design, but I know I can't prove it. And somebody comes along and says it's just chance. There's no really convincing argument that I could use to show that they're wrong.
You can only say it looks like a design.
Yeah, it looks like, to me, it looks very convincingly like design, almost compellingly like design. But nonetheless, I do concede that in fact it could be. Perhaps it could be chance. So, you've got to say that. It's up to the individual to assess the evidence and make their own inference from the evidence, to design if they want to, or if they want to say a chance, they can say a chance. Anyway, so, that's... but as far as the evolution of life is concerned, in this universe, clearly in this universe, there's a special fitness for life like us. And that fitness long preceded Darwinian evolution. It was there in the properties of matter before the formation of the Earth. It was sort of, Freeman Dyson once says, the universe must have known we were coming. From the same sorts of reasons, right? Yeah. So anyway, we're straying a long way from, of course, evolution at the moment, but
that's fascinating.
Yeah, I mean,
basically,
like the design of the lungs, the design of the cell, a lot of that looks as if it's in a primal blueprint. And I think it's been fine-tuned to some extent by selection. In other words, the exact direction and the exact form. For instance, we have proteins and we have DNA. It may be that you could make another molecule with the properties of DNA. It may be that you could make another property with the properties of the proteins in the cell. That's possible. But they'd have to be similar to DNA and they'll have to be similar to proteins because they're constrained by the same atoms and the same basic processes. For instance, proteins are stabilized and folded because of the hydrophobic force. Because some amino acids have little fatty chains on them, and they're forced into the center of the protein as a cluster, as a sort of insoluble cluster, and that stabilizes proteins. And those sort of forces are going to be with you however you start designing complex macromolecules. Those sorts of processes like the hydrophobic force are going to be there, and you probably have to use them in some way. Yeah.
So listening to you, I'm asking myself, why is it the fact that, for example, children at schools are not, well, perhaps not taught, but even told about all this? I mean, there is a general conviction that Darwin's theory, going back to Darwin, that Darwin's theory is absolutely proved, it's indiscussible, it's certain, it's obvious. And even if you just mention that perhaps we should taught our children about doubts, not about, denying it completely, but about some doubts. Well, you are a religious fanatic. This is the most frequently appearing insult.
All I would say is that, in fact, people who say that are secular fanatics, if you see what I mean, okay? It's just two types of fanaticisms. Let me also say that as I was preparing for this book, there was not only the experiences with the red cell and looking at other biological phenomena. When I was preparing this book, the cosmologists were looking at the cosmological constants, and they were proposing the anthropic principle. You probably, okay. And
I think some of my viewers heard about it.
Yeah, and so basically, it's extraordinary. For instance, gravity is 10 to the 40 times weaker than some electrical forces in the atom. If it was very slightly different, there'd be no stable solar systems, no planets, no suns, nothing. The whole universe would be a chaos, right? And people like Paul Davies, Martin Rees, Gribben, they wrote a series of books. I mean, the book I read was by Paul Davies, which is The Accidental Universe. And in the beginning of that book, he says, looking at the constants of physics, the impression of design is overwhelming. Okay. Now, Paul Davies is no Christian. I don't even know whether he's a theist. But he makes that point, and it is a shocking and it's a disgraceful thing that kids in schools don't know about the extraordinary fine-tuning of the constants of physics, because this is out of biology, right?
I like what you're saying. Yeah. You're saying perhaps this all happened by chance. Yeah. You have to decide, but you have to know the facts. You have to know the proofs.
Yeah, but anybody who knows the facts about the constants of physics can see that the design inference is a sensible and rational inference to make. Okay? I mean, you can make the chance one as well, but you can also make the other one. And so that, in fact, kids in school should know about these facts about the physics of the world. And this is not biology. The fine-tuning in biology is like the properties of water. Water is fit for the hydrological cycle. It's fit to make the matrix of the cell. It's fit for the medium of the circulation, and so forth. It's got the hydrophobic force, which is fit for erecting complex things in the cell. So water is fine-tuned for all sorts of biological reasons. It's also fine-tuned by its thermal properties for your warm-bloodedness. It's got a high specific heat, and you lose a lot of heat on evaporation of water. So water is fit in so many different ways for all sorts of different biological phenomena that it's once again, we're thinking of these like the cosmological constants that, when Paul Davies said the impression of design is overwhelming, if you look at water, oxygen, carbon, it's the same thing. The fine-tuning is so amazing. The impression that you get of design is pretty overwhelming. That's for me anyway. And if kids knew this all in school, that would be the way to go. The way to go would not be to criticize necessarily Darwinism, but to present the fine-tuning from the cosmological constants all the way down to the properties of water. And that would be not theological. It would be just the facts of nature as revealed by the last 50 years of science. Yeah.
And it seems to me to be quite a reasonable expectation.
Yeah.
Just to close our interview, I would like to ask you a general question about how science is perceived today. Because we quite often hear the phrase, trust the science. Can we, in your opinion, can we speak about something like one science? Does it make any sense to tell people they should trust the science as if there was just one science?
I've been guided all my life since I did my PhD years ago at King's by science. And I mean, we started this interview by talking about Darwin as a hypothesis or theory. Science is full of theories and hypotheses, and there's been some crazy ones that have. I mean, there was the theories of phlogiston, and there was all sorts of crazy theories in the past. But science keeps advancing, and eventually, I believe in science. I believe science ultimately finds truths about the world which we can't dispute. But Darwinism is certainly not a truth about the world. It's a theory. It's a hypothesis about things, right? But the fine-tuning we're talking about is discovered fact, okay? And for me, I know there's a lot of people talk about scientism, and you know that in fact there's too much sort of anti-religious, anti-theological. Sort of it's got into the scientific worldview, and kids are taught science that it's, you know, religion's completely out of bounds and things like this. But for me, I do ascribe to science, and I think, I mean, there is one. You go from Copernicus, who wrote something very important not far from where we're sitting. Basically, from Copernicus all the way down, science is slowly, perhaps fitfully, but it slowly moves towards a true description of the natural world. So, to me, there is one science which is based on, you know, observation and then deductions and things like this, and that's the scientific method, and I trust it. But, you know, it's amazing. I'll tell you how strange it is, how science can change its view. For instance, in 1960, nobody believed in continental drift. If you mentioned you believed in continental drift in 1960, you'd have lost your job at a university. In 1970, if you didn't believe in it, you'd have lost your job. And I remember watching the discoveries that were made by the geologists when the geological world went from fixed continents, immobile continents, to mobile continents, a dynamic view of plate tectonics, right? And that was a 10-year, one decade, complete change, right? So, and to me, that was a triumph of science. They did measurements in the sea, and they did all sorts of measurements, and they came to the conclusion, yes, the continents do move. It's one centimeter a year. It's not very fast, but nonetheless, they do move, and it's a fact. Yeah, and that's how you can see that South America and Africa fit together. They moved apart. Yeah. So, you know, I do believe in science, and it's science which convinces me that Darwinism can't give a comprehensive explanation for the biological world. It can do a lot, and that's okay. Yeah, I think selection is an important factor, but there's a lot of other elements as well, from self-organization to the properties of matter, which are going on in biological systems, which are outside of the sort of the spectrum of Darwinism. You know, it's a different thing. Yeah.
Mr. Denton, thank you very much for being my guest.
Okay, well, it was a pleasure. I hope I didn't get into too much deep water.
I think it was understandable.
Okay.
Bardzo dziękuję. To była rozmowa niekontrolowana. Moim gościem był Michael Denton, autor książki Kryzys, teorii, ewolucji oraz wielu książek, które przyszły po tej właśnie. doktorat na King's College, współpracownik Discovery Institute. A to była rozmowa niekontrolowana. Łukasz Warzecha, kłaniam się Państwu. Do zobaczenia.